Okay, so I am here to tell you about something called expected value. Expected value is a concept from probability, and it's used a lot in games and in financial planning and a lot of other areas. You are going to be using it in this class to design a game and decide whether the game is fair or not. But first, let's talk a little bit about what it means. Now, to understand expected value, you have to know a little bit about probability. Assuming you already have a basic background, but to review two key ideas. First is theoretical probability. Theoretical probability is the probability based on what you think will happen. I think that if I toss a coin, there are two things that can happen, heads or tails. If I want to know the probability of one of those things, well, the number of ways I can get heads on a coin toss, there's only one. The number of things that can happen on a coin toss, there's two, heads or tails. They're both equally likely, so the probability is the number of ways to get heads, 1. The number of things that can happen, 2. Divide them. Put the number of ways the thing I'm talking about can happen in the numerator, put the total number of things that can happen in the experiment in the denominator. My experiment is a coin toss. I'm putting it out there that I think my theoretical probability is there is a 1/2 or 0.5 probability that I will toss heads. That's theoretically. Then there's something called experimental probability. Now, experimental probability is what actually happens. It's not what you think will happen. If I toss a coin 10 times and the coin comes up heads 8 times, then as far as I'm concerned, the probability of flipping heads with that coin on a coin toss is 8 out of 10. Because the outcome for which I was observing occurred 8 times, and there were 10 trials. So that is my fraction, that is my probability. Theoretically, I think I should have gotten heads half the time. For whatever reason, it didn't happen. But the experimental probability was 8 out of 10, or 4/5, or 0.8. If you're running an experiment, you have to go with the experimental probability. You can't write down the theoretical as a result. What does this have to do with expected value? Well, expected value is the theoretical average result of repeating any observable action. It's what you think will happen, what the theoretical probability predicts will happen if you keep doing the same thing over and over and over again. It's based entirely on theoretical probability. Let's do an example. You decide to buy a raffle ticket. There are 100 tickets, and there are 3 prizes. The first prize ticket is $50 if you happen to get that one lucky ticket. There are 4 tickets out of these 100 that will give you a $5 prize. There are 5 tickets out of the 100 available that will give you a $3 prize. Each ticket costs $1. So the question is, what is the expected value of buying a ticket? Now, this won't work as a predictor for any individual raffle drawing. The point of this is, if you go to this exact same raffle week after week after week, what do you think the long-term outcome will be? Well, to do that, we have to do a little bit of math. And I have a way to do that. Okay, this is one of my favorite calculators. It's entirely visual. And we are going to work out the expected value. So what I need to do to find the expected value, I'm going to take this top prize ticket. That has a value of $50. But I'm not often going to get $50. That should happen if all goes according to plan, if the theoretical probability is correct. That will happen 1 out of every 100 tickets I buy. I should have to do this 100 times to be certain to have this $50 happen. Now in real life, that's probably not how it'll play out. There's no guarantee that if you buy a ticket 100 times, you'll ever get the $50. Shouldn't be surprised if you win $50 on the first try either. But we're talking the theoretical probability right now. In theory, I should have to run this experiment 100 times to get the $50 prize. But then there's the $5 prize. How often should that happen? Well, that should happen 4 times out of every 100 tickets that I buy. This $3 prize, that should happen 5 times out of every $100 I buy. These come out to an anticipated average of 85 cents. Now, does this mean if I play the lottery over and over and over again, sometimes winning $50, sometimes winning $5, sometimes winning $3, I should average 85 cents of profit? No, because when you don't win one of these prizes, it's not like nothing happened. In order to be considered for these prizes, you had to buy a ticket that cost $1. That has a value as well, a negative value. So I need to subtract $1 multiplied by the probability that I will lose that dollar. And the probability that I'm going to lose is 90 out of 100. How do I know that? Well, there's 10 winning tickets, 90 losing tickets, 90 out of 100 theoretical probability that I'm going to lose. And this gives me a new expected value of negative 0.05. Here's what this means in real life. If I buy 100 tickets and I win once, win big once with $50, I win little 4 times out of these 100 tickets that I buy, I get $5. I win a little less, 5 times, I win $3. But 90 times I lose this dollar. So if I were to play this particular raffle over and over and over again, I should expect to, on average, lose a nickel per raffle. Notice this possibility is not even a thing that can happen on one run through the lottery. Can't happen through this raffle. I mean, if I play this raffle once, I'm either going to get $50, $5, $3, or I'm just going to lose my dollar. So this can't happen any one time you play. But it's what you should anticipate happening on average over multiple extended periods of time playing this game. I'm going to insert this into my document, take a little capture of it, and there it is. Let's see. Here's where I asked the question, so, okay. Here's my math, and here's my statement, which will be my interpretation of this in a slightly smaller font. Based on this math, if I were your consultant, you were asking me for advice, I would say you should expect to lose a nickel on average playing this raffle just repeatedly. That's my conclusion based on determining this expected value. Continuing with expected value. What is the expected value of rolling a single die? Well, when you roll a dice, there's a limited number of things that you think of that can happen. You can roll a 1. You can roll a 6. You can roll another 6. You can roll a 5. Now, if this were an experiment, I would be recording these, and the expected value would be whatever the average value of all these rolls was. But theoretically, what should we expect to happen? Well, when you roll a dice, there's really 6 things that can happen. Let's go back to our calculator to think about a die roll here. I could roll a 1, and that should happen 1 out of every 6 times I roll the dice. I could roll a 2. That should also happen 1 out of every 6 times I roll the dice. I could roll a 3. Should happen 1 out of every 6 times. That would be an expected value of 1, but there's more coming. I could roll a 4. That should happen once out of every 6 tries. I could roll a 5. Try that again. I could also roll a 6, and the expected value of rolling a single dice over and over and over again is 3.5. Now again, this isn't even a possible thing to do if you roll a dice once. Now, even on this little simulated computer screen dice, I guarantee this thing is never going to come up 3.5, no matter how many times I roll it. But if I keep rolling it over and over and over again and add up all the different numbers and divide it by the number of times I rolled, the average should wind up being pretty close to 3.5. In fact, there's a little law in probability that says if you do something enough, the experimental and the theoretical probabilities should eventually start to match. So the experimental value, expected value, rolling a die should be 3.5. Okay? Now, what does this have to do with the game that we're going to use as an example to teach fair or unfair games? First off, what is fair? We'll talk about that in a moment. So what is fair? A game is fair if everyone begins with the same theoretical expected value. Okay, so what does that mean? Well, to begin with the same expected value means the results have to be totally up to chance. This can be a little bit harder to design than you might think. If we look at a game that's based entirely on the roll of a dice, on average, if you roll a dice a lot, you should expect the die rolls to average 3.5 per roll. Now, you won't get this on any individual roll, as I mentioned before, but if you roll a dice enough times, add up the numbers, divide it by the number of times you rolled it, the more you do it, the closer you should get to 3.5. This should happen to everyone, regardless of who is rolling the dice. A game based entirely on rolls of the dice should be fair. Now, this raffle that we talked about, this had an expected value of negative $0.05. You lose a nickel every time you play, if you play it over and over and over again. Again, that's not possible any one time you play the raffle, but play it enough, you should start finding yourself down an average of 5 pennies per time you play the raffle. This is unfair. This is meant to be unfair. You have to lose money for this to work. You just have to. No other thing that can happen. Raffles are designed to raise money for someone else. You playing them is supposed to turn out badly for you in the long run. Otherwise, charities, churches, other organizations, schools that run raffles, there'd be no point to doing it if they didn't gain money at your expense. Now, I want to look at a fair game that relies entirely on a dice roll. That should be a fair game if everyone rolls a dice. And I'm going to play against a computer, and I'm going to test the theoretical fairness versus the actual fairness of the game. So a game is fair if everyone begins with the same expected value. If you take a look over here, I've got a spreadsheet I've made called Backgammon. And this may be a little hard to see on smaller screens, but I've put here every possible die roll. But wait, what if you don't know how to play backgammon? Well, let's take a quick look. Here is an iPad backgammon game. It is me against the computer. The computer's named iPhone, even though it's off my iPad. It is set to easy, and I'll be playing the white pieces. If you've never played backgammon, then first thing you need to know is you pick a color piece. These white pieces that I'll be playing, they have to move counterclockwise down the length of the board as you follow the cursor. They have to cross the board, and they have to go all the way to this other side. Then they can begin leaving the board. The black piece is controlled by the iPad. They'll be going clockwise around the board, and they'll be leaving the board this way. First player to get all the pieces off the board wins. This is based entirely on rolling the dice. Roll 2 dice. That determines how far your pieces can move. There's a little bit of nuance to it, but that's the gist of it. Now, there's one slight thing that's different about the expected value of these rolls. I can't just say, based on my earlier math, hey, every time we roll a dice, over and over and over again, the average should be close to 3.5 points, or 3.5 spaces moving my pieces on a backgammon board. That's because if you double your roll, if I get 2 1s, that does not allow me to just move 2 spaces, that allows me to move 4 spaces. If I double my 2s, they're worth twice as much. I can move 8 spaces. If I double my 3s, I can move 12 spaces, all the way down to, if I double my 6s, I can move 24 spaces. Now there's some nuance to backgammon still. There's an ability like in checkers to catch the other player's pieces and send them back. There are ways to trap a player up here that'll throw things off a little bit. But here is my expected value. See, when you roll 2 dice, if you look at these die rolls here, you can get a 1 and a 1, you can get a 2 and a 1, you can get a 1 and a 2, which mathematically, this 1 and a 2 is a completely different event from this 2 plus 1. Sounds weird, but in terms of math, that's how it works. There are 36 things that can happen. And the value of each roll I placed over here. If I roll a 1 plus 4, that's a value of 5. If I roll a 2 plus 6, that's a value of 8. But if I roll a 3 plus 3, that's not a value of 6, that is a value of 12. So I add up all these values all the way down to the 6 plus 5 dice roll that gets me 11 points, and the 6 plus 6 roll that, because it's a double, gets me 24 spaces of movement. And I divided that by 36, and I determined that I should expect to average 8.16 repeating moves per die roll. I'm not sure if that'll happen. Okay, so let's play this game of backgammon and let's keep track of the rolls and let's see if this computer on easy mode is actually fair. So, start a new game and we'll roll. And I've won this roll. I certainly think that's fair. I rolled a 5 plus 3, and I'm going to use that roll to set up a little bit of a defensive position, try and block them from moving. Now the computer just rolled a 2 plus 3 and moved its pieces accordingly. Now, let's see, I'm going to roll a 6 and an 8. So I'm going to use that to move this guy over to there, and the computer just rolled a 6 and a 4. So let's keep track of these rolls. Now, it occurs to me this is probably not particularly interesting for you guys out there, so I'm going to continue this on my own, and we will speed this up a little bit. That didn't take so long, did it? Now, let's take a look at what happened here on easy mode. We had these rolls, and I rolled a certain amount of luck, computer rolled with a different amount of luck. Let's take a look at the expected value. We'll take a moment and calculate that. And once again, I'm not really super sure that you guys need to be here for this part. So, okay, so after some rapid calculations, I can now look at this and I can say what I have here. Okay, here's all the die rolls. Now, this value down here is my experimental expected value. What I did is I took all of these values and I multiplied each one of them times the probability that they would occur. So, after adding all these up, so what that does is that tells me is, it's the same thing as you do when we did when we calculated the dice expected value over here. Okay, we got this 8.167 by adding up all the things that could happen, multiplying them by the probability that they would. Well, this is what actually did happen instead of what could happen. And I got a lot lower than that 8.16 repeating. I got 5.6 repeating. So the game didn't do me any favors. It didn't give me rolls that were as high as, frankly, they should have been if this had been truly random. In fact, the game gave itself a higher expected value. the game gave itself more of a benefit than I did. In a straight-up race of its pieces to the end versus my pieces to the end, I should have lost. Now, I did place my pieces a little bit more strategically, and one other thing happened. I occasionally captured its pieces. This yellow roll I indicated did not count for the computer because it was captured, stuck on the bridge in the backgammon game. This roll did not count. This roll didn't count. This roll didn't count. This is where some doubles occurred. All of them did, in fact. I think maybe what this particular game does is it handicaps the computer pieces when you're on easy mode by giving them their best rolls when they can't use them. In fact, over here what I did is I gave the number of places that the computer's pieces could move, the dice roll values of the computer, and I added them up again, but I left out the ones that it couldn't use because it was trapped. The computer got some of its best rolls when it could not use them because it was trapped on the bridge. So when I take those values out, the computer actually only averaged 4.361 repeating per die roll, much less than what I did. So that's another piece to how I won. So how does the computer... The point to all this is if you're going to play a game on easy mode, where the computer should lose to you if you have any idea what you're doing, well, then the computer has to do something to make the game unfair in your favor, unfair to itself. In this case, it did not use expected value. The computer gave itself a higher expected value. It controlled these dice rolls and it made them spit out more value per roll for itself than it did for me. But if you take out the rolls that it couldn't use because I successfully trapped these pieces on the bridge, the computer's average per dice roll suddenly goes down to much lower than mine. So that's one way that game developers can make a game unfair to get an outcome they want. This is going to, for your assignment, you are going to need to play Backgammon Online on easy mode, medium mode, and difficult mode, and you are going to have to easy, medium, and hard if you use this game, and you're going to record your rolls, whether you won or lost, which ones were you unable to use the roll, which ones were the computers unable to use the roll, and we're going to try and figure out just what a video game does, simple video game like Backgammon on iPad does, to make a game fair or unfair. We'll do that next time. Hopefully now you have a better understanding of expected value, and we'll pick it up from there.